screencast that was posted for that day, a quiz as well. So that lecture was based on starting module 2, which is the structural elucidation of compounds using spectroscopy. And spectroscopy is the interaction of light with matter. So light is many different things. There's an electromagnetic spectrum of light. So you have radio waves on the low end, X-rays, gamma rays on the high end. And they interact with atoms and molecules differently, and they produce different pieces of data that we use. So module 2 started with mass spectrometry. So spectrometry is not exactly spectroscopy. So mass spectrometry is interacting in a different way with the molecules. And essentially what it is telling us is the molecular weight of a compound. So in the Wednesday's lecture, what we did was looked at sort of the fundamentals of elements, isotopes. If you're not terribly familiar with what isotopes are, please review there's a couple slides in there and go back to your Gen Chem book. The isotopic abundances of the natural elements are really the key to mass spectrometry. And we'll look at an equation today that's going to help us determine the exact number of carbons in a molecule from the parent ion. So I'll review what the mass spectrum data looks like, and then we'll keep going with that molecule testosterone, which is a steroid. And we'll do this thought experiment where we're kind of pretending we don't know what the structure of testosterone is, but we're going to use the parent ion mass, convert that into a molecular formula. So at this point, things are going to slowly start ramping up in difficulty for the course. In the sense of we're not going to focus a lot on memorizing things, we're going to focus our attention on developing an intuition of solving problems given pieces of data. And so with the data, we always have to make sure that it sort of makes sense. We don't want to propose something that violates a piece of data that we're seeing. So we'll do mass spec today, and then Monday and Wednesday we'll do infrared spectroscopy. Any questions before we get started? Seeing no questions. Well, how many people know what Robert's rules of order are? I didn't know until I actually started sitting on committees here at USM. You should look it up. It's boring, but that's how meetings are run. We're going to make sure everyone's satisfied before we move on. So mass spectrometry, why do we use it? Essentially, again, it's going to give us a mass, and from that mass, we can determine a molecular formula, and I'll just abbreviate that MF for the most part. And since this is organic chemistry, we can always be 100% confident the molecule is going to have carbon and hydrogen. And so some numbers to commit to memory is carbon has an atomic mass of 12, hydrogen's 1. But, you know, in recalling the screencast on Wednesday, these elements can have isotopes. And isotopes, they differ in the mass. So sometimes you'll see things like this, carbon 12, carbon 13. So the difference between those is the C13 has an extra neutron in the nucleus. And then there's another isotope, carbon-14. You've probably heard of that. It's a radioactive isotope. So it has 2 extra neutrons, and because it's radioactive, it's emitting a particle at all times that eventually the nucleus decays. Hydrogen is 1H. It has 2 isotopes, 2H, which is typically abbreviated as D for deuterium, and then a third one, which is T for tritium, and tritium is radioactive as well. So these isotopes all exist in nature, but their percentage differs. And the percentage is what matters as we move forward for not only mass spectrometry, but also when we get into nuclear magnetic resonance spectroscopy, because those look at specific isotopes of those elements. That's what's being detected. So we know that there's C and H, but what about the other heteroatoms? And as explained on Wednesday, again, a heteroatom is anything other than C or H. So we have nitrogen, oxygen, and then the halogens. As explained on Wednesday, if there's an odd number of nitrogens, the mass of the compound will be odd. So you're just looking at the parent ion. Is it even or is it odd? If it's odd, it's going to have an odd number of nitrogens in the molecular formula. If there's an even number of nitrogen atoms, then the mass is going to be even, and things get a little bit more difficult to figure out. We'll spend today talking a lot about oxygen, because that is a little tougher to figure out. But as we learn more of these analytical techniques, specifically IR spectroscopy, that will help us confirm that an oxygen atom is present. You have a question?
Yeah, what does the D and the T mean next to the H of the hydrogen?
D stands for deuterium, T stands for tritium. The halogens, 2 of them show very unique signatures. So chlorine and bromine show unique signatures in the mass spec in terms of their isotope ratios. Fluorine and iodine do not. We'll talk about Cl and Br a little bit, maybe on Monday. So really the mass spec has signatures for nitrogen, chlorine, bromine, and iodine. Oxygen's a little challenging, and fluorine we're not going to worry too much about. So getting back to oxygen in terms of what we're going to do today, we want to figure out exactly how many carbon atoms are in a molecular formula using the parent ion of the mass spec. From that, we can figure out the carbon contribution to that total number. We just multiply by 12, and then we're going to do just some simple addition, subtraction, and develop an intuition of, okay, of the total mass, this much belongs to carbon, and then we can do some thinking about what is the ratio then of hydrogen to oxygen. And then once we have the molecular formula, something we're going to do, again, quite a bit, is calculate degrees of unsaturation using CnH2n plus 2. And then probably something that's a departure for a lot of the learning you've done so far in all of your classes is we're not going to just get to the right answer. We're going to make proposals. It can be this, that, or the other thing. And then we're going to look at the data and see how the data best supports one of those claims. So just to review the mass spectrum data, there again is the structure of testosterone. And it's a steroid. These exist in your body, so your body makes them. It's a hormone that will trigger a biochemical process to start, continue, or stop. So I chose testosterone because it's an anabolic, androgenic steroid, and people will use it for gains if you're a gym bro, or athletes use it to dope. It'll essentially increase muscle mass, make you stronger, faster, that sort of thing. And so the piece of data that's shown is, for a way of categorizing it, is a molecular fingerprint. So in terms of forensics, you do fingerprints. Everyone has a unique fingerprint. Every compound will have a unique mass spectrum. And we're really interested in only two pieces of data for this class. On the x-axis is M to Z, where M is the mass and Z is the charge. So the red lines that you see, those are signals. And for our purposes in this class, Z is going to be +1. So everything that you're seeing is an ion. So it's an ion in the +1 state. The y-axis is the relative intensity or the abundance. It just means how often you see those ions. So if we start at 0 on the x-axis, that's 0 mass. The first thing we want to look at is the highest number. And so for here, that number is 288. And you'll see up at the top here, it says the exact mass is 288. So the mass spectrum is telling you the molecular weight of what you're seeing in all of the elements that compose the molecular formula. So what we want to figure out is, given the number 288, can we backtrack and figure out the molecular formula? So 288 is called the parent ion. And so that corresponds to all of the elements in the ratios of the molecular formula. That's the highest mass. So it's called M. And so the plus, again, that's your charge. It's, for our purposes, it's always 1. If you go in to study more larger biological type molecules, the charge can change, and then it gets a little bit more challenging to interpret. So anything with a mass less than the parent ion is called a daughter ion. So everything that you see from 0, up to here, those signals result from the parent ion. So the way the instrument works, you have your sample, it goes into the instrument, it forms the parent. Because that's an ion, it's higher in energy, and it's going to start falling apart. It falls apart in different ways, and those are called daughter ions. And so you see these like groups. They're called clusters or envelopes. And so they're just clusters of smaller masses from these fragments that happen. We're not going to worry too much about interpreting them, but the only other thing we need to look at is something called the base peak. The base peak is the peak that has 100% abundance. And as we see on the y-axis, there's 100%. Really what you're doing is just scanning over, and then you see you have this signal at 124. That's the most abundant peak that occurs from the parent. So the base peak most often is not the parent peak. It's something else. So you see the intensity of that parent, if we scan over, is 80%. So just keep in mind the nomenclature that we're talking about. So what does that mean? So there's the 288. And then this next peak is the 289. And then you have this little blip there, that would be 290. So that little blip at n+2, if it was chlorine, you know, the intensity would have to be somewhere up here, about 1/3 of the parent. If it was bromine, you would have an equal intensity to the original M parent. Since we do not see that, we can eliminate chlorine and bromine being present. So the question or the problem we're trying to figure out is if you're given the mass and you don't even know what the structure is there a way to calculate the molecular formula? And the answer is yes, and that's what we're going to walk through is the logic of doing that. So since the parent ion is 288, that's an even number. As we saw in the Wednesday screencast, we can rule out from the molecular formula an odd number of nitrogens. The other elements that we can rule out are chlorine and bromine. So if we're using this nomenclature of the square bracket, M plus the plus sign as the parent, things that occur at higher masses after that, we would say M plus 1. So for 288, if that's the parent, M plus 1 would be 289. Chlorine and bromine both have significant M plus 2. So you're looking at the parent, you're scanning 2 mass units over, and then you're looking at the ratios or the intensities. Does anyone remember what the M to M plus 2 ratios for chlorine would be? 3:1. And then bromine would be 1:1. So that's a visual thing, just looking at either the heights or comparing the actual abundance numbers. Iodine has an atomic mass of 127. So if it was present in the molecular formula, you would see a signal at 127. We don't see that, so we can eliminate iodine as well. Fluorine's a little challenging, so we're not going to delve too much into fluorine at this point. So we've eliminated nitrogen, some of the halogens. Now we're left with this conundrum of oxygen. And to help us get to a right answer faster, or a best claim, we're going to use this equation here that says the exact number of carbons is equal to m plus 1 divided by m, and then all of that divided by 1.1. So what does this mean? The m plus 1 and m are not the masses. They're the ratios, the numbers you get from the y-axis. So those will either be given to you, or you have to just sort of draw a line over and approximate what it is. The 1.1 number comes from the C13 isotope natural abundance. And so C12 to C13, most of the carbons in our body are C12. So that's 98.9. And then the C13 is the 1.1. So the way that, the International Association of Doping or something, the way that they catch athletes doping steroids, your body produces testosterone with a certain ratio of C12 to C13. If you're taking a synthetic steroid, it's going to have a different ratio. So when they analyze the urine, they're going to compare, does this match the normal ratio of a biological process within this certain error? If it's outside of that error, they can say, yes, this person has been doping this molecule. So let's take the numbers from that mass spectrum for testosterone, and we're just going to plug it into this equation. And so again, notice the numbers that we use are the percentages we get from the y-axis. They're not masses. So that m plus 1 is 20.5. The m is 100. And then we divide all of that by 1.1 because that's the C13 contribution. And so when you do that, what do you get? So like this number, 18.63. We're going to round that up to 19. So we'll say B is the right answer. So one thing to point out in terms of the intuition, this m plus 1, see how it's 20? That's giving you an idea of what the exact number of carbons should be around. So if you're saying, well, it's 10 or it's 25, that's sort of outside of the bounds of what the m plus 1 peak is telling you. So we get 19. And the parent is 288. That's the total of everything. So how much of that is carbon? So 19 carbon atoms times
12 for the atomic mass. So 19 times 12. Which answer is the best one? Huh? 228. So 228 of the 288 is due to carbon. So now we have to figure out how many hydrogens and then basically how many oxygens. So 228. So to recap, again, we took the numbers from the y-axis. We got this 18.6. We rounded to 19. 19 times 12 is 228. And so we're slowly zeroing in on what the molecular formula could be.
Yeah, like where did you get that? Like, I know you did them for the y-axis, but I don't see like where you pulled them from on the graph.
So these were, the parent was not shown as the base peak. It was shown as like 80% or something. All I did was scale it to 100 to make the math a little bit easier for everyone. So now we're going to return to, question.
How did you get the 125% from the graph?
The what? So we're going to return to this degrees of unsaturation exercise to help us now determine what is the maximum number of hydrogens we can get for 19 carbons. And then that's going to put an upper limit on the hydrogens so that we sort of know where we can work with in terms of the mass that's left over. So we have n equals 19. We plug that into the 2n plus 2, so that gets us 38 plus 2, that's 40. So the maximum number of hydrogens could be 40. So we said M is 288, C was 228, the max H is 40. Now if we add those, we get 8, 6, 2, 268. You see how it doesn't match 288? So what that is telling you is there's a heteroatom present. The difference between 288 and 268 is 20. So to recap, how much mass is unaccounted for? We have 20 atomic mass units that are something else. And so with our abbreviated periodic table CNOF, there's the atomic masses 12, 14, 16, 19. So we've already done the carbons, we can eliminate that. You can see that 14, 16, and 19 do not exactly equal 20. So that is further telling us that we do not have 40 hydrogens. We have less than 40, and then we have some other heteroatom present in some ratio. So to recap everything we've done, we use the equation to calculate 19 carbons. We multiplied that by 12 to figure out the mass contribution. That gave us 60 remaining from the 288. We used degrees of unsaturation to figure out there could be a maximum of 40 hydrogens. That would have a mass contribution of 40, and then we're left with this excess of 20. So now what we have to do is figure out the exact ratio of hydrogen and oxygen. So if H is 1 and oxygen 16, if you had one oxygen in there, that's only 16 mass units. So 20 minus 16 gets you 4. We know we cannot have 44 hydrogens because the max is 40. So we just set up this little table here. Where we're looking at different ratios now of the oxygen to the hydrogen. And so in the oxygen column, we're just increasing from 1 to 2 to 3 to 4. And then the hydrogen, we're seeing what then is the difference. So we had this 60 atomic mass units to account for. You take 1 times 16, you get 16, 2 times 16, 32, etc. And then what I'm doing in the hydrogen column is taking 60 minus that number to get the total number of hydrogens. So we already said A is wrong. Because that's past the maximum hydrogen number we can have. For 2 oxygens, we would then get 28 hydrogens. 3 oxygens, we would get 12 hydrogens, and then D has to be wrong because we would end up with a negative amount of hydrogens because that's 64. That's already past the 60 we're trying to figure out. So really we're left with 2 choices. So C19, H28O2, or C19, H12O3. So from that, we have to choose which one's best. And now what we can do from those 2 is calculate degrees of unsaturation and see if one's more reasonable than the other. And we already figured out that for 19 carbons, there should be 40 hydrogens. So we know from our prior learnings that oxygen doesn't affect the hydrogen count. So that just becomes C19H28. This becomes C19H12. We calculate degrees of unsaturation, H40 minus H28, that's 12. Divide that by 2. So that gets us 6 degrees of unsaturation. And then what do we have? 40 minus 12 is 28. Divide that by 2, that's 14. Question?
Why did you just assume that it's oxygen? Why can't we assume it's fluorine?
Why don't we assume it's fluorine?
Why did we assume it's fluorine?
Because fluorine's a little bit more difficult in terms of this thought process. We're going to need other pieces of data, particularly NMR, which we'll learn, at the later part of this module. So fluorine is one we're going to have to circle back to.
Just assume, even though we don't know.
Correct. So of these two, the better sort of claim is going to be this first one with the lower degrees of unsaturation. And when you have 19 carbons and only 12 hydrogens, that's giving you this large number of degrees of unsaturation. It's going to be really hard to start proposing things because you're going to have to put a lot of rings or double bonds in there to match what you're given for the data. So to recap the steps in solving this problem, the intuition we're developing, we had to account for those 60 mass units, setting up this table of the different quantities of oxygen that could be present, which then affected the number of hydrogens. And so we get, for 1 oxygen, an unreasonable number of hydrogens. For 4 oxygens, we would have to have negative number of hydrogens. We had these 2 claims here that were reasonable. 2 oxygens makes the most sense because 3 is going to have a large degree of unsaturation for the carbon count. So when we now circle back to look at the structure and the mass spectrum, we said there were 6 degrees of unsaturation. We can see there's 4 rings and 2 pi bonds. So the difference between 14 and 6 is 8. So of that sort of backbone, you would have to add 8 more degrees of unsaturation somehow, and that would be pretty difficult to make a reasonable structure. So as a sort of check-in, pi bonds can be carbon-carbon, carbon-oxygen, or carbon-nitrogen. For this type of pi bond right here, what functional group is that a part of? A ketone? So a carbon-oxygen pi bond is called a carbonyl. For the carbonyl groups, since there's so many of them, you have to look at what's bonded to it. And we see we have a carbon and another carbon, so that makes it a ketone. And as we move forward with spectroscopy, there are a lot of functional groups with oxygen. And so a reasonable question would be to ask, if you did not know the structure, how would you know that that oxygen is present in a ketone? That's where infrared spectroscopy comes into play, because that carbonyl group is going to give a specific looking stretch. In the way that I teach IR is it's visual. The signal is going to look a certain way on a certain region of the spectrum. So if you're going into like some healthcare career, and you think of like X-ray, like how do you know a bone is broken? Well, you have to look at enough pieces of data to say, okay, this, whatever the wrist to the elbow, whatever bone that is, this is a normal set. It's a healthy looking bone. And then when you see one that is broken in any sort of way, you say, okay, this one does not look normal, so therefore something's wrong with it. And that's how IR is. You're saying, okay, this functional group is a carbonyl. It occurs in this region and it looks like this. Is it there? Yes. Is it not there? No. And so from that, you develop this intuition about, okay, there's a molecular formula now. It could have a carbonyl or it doesn't. So any questions before we run through another case study? Yes.
So what can't we assume there's an even number of nitrogen?
Say it again.
We assume there's an even number of nitrogen.
If there's an even number of nitrogens, again, that gets a little bit more challenging. I don't anticipate throwing any sort of, those more specific problems at you, either on the quizzes or the exam. So Module 2 has 2 exams. I believe one is next week. That focuses only on mass spec and IR. Then the second exam will focus on NMR. So I broke it up that way so that it's not too overwhelming in terms of all of the concepts for one exam. Any further questions before we move on to another case study where we put all of this into practice? So over the remainder of the lecture, we're going to look at this prompt. So given the parent ion with a mass to charge ratio of 72, we're going to say that peak is 100% abundant. Again, just to make the math a little bit easier. The M+1 has a mass to charge of 73. So that's what the +1 means. It's 72, 73. And the abundance of that is 4.3%. So we're going to run through all of those activities we just did. So notice there's no structure shown. We're going to find a molecular formula, and then from that, start proposing some structures. And then as we move forward into IR and NMR, we'll sort of return to this problem where we can then narrow it down based on other pieces of data that we're given. So there's a little table just stating the prompt in a different way. Given that data, which of the following heteroatoms is most likely present? Huh? So students often, there's a subtlety which I'll draw on here that for whatever reason, it's sort of students walk into that or fall off that cliff. It's not D. Could it be A, nitrogen? So 72, is that even or odd? It's even. So we're going to eliminate nitrogen. If it was odd, then it could have nitrogen. The sort of trap that students walk into, see how this says M+1? And then this says M+2. So again, M+1 just means you're adding one mass unit to the parent. +2 is 2 mass units. The chlorine and bromine they're always +2. So because it says it's +1, you can eliminate those right away. So why are these ones different? Again, notice the difference in those isotope abundances. 37 minus 35 is 2. 81 minus 79 is 2. That's what that +2 means. This +1 right here, again, that's from the C13 contribution. Question?
What does that say about what's your category about like the 72 and the 73?
M to Z. And so, furthermore, we said chlorine would be in a 3-to-1 ratio, bromine 1-to-1. Now, how that translates into these abundances. So, again, I'm just going to write down an abundance number. If this was 100 for chlorine 35, then the chlorine 37 would have to be 33. For bromine, it would be 1-to-1. So I just wrote down 100 and 100. But if it was like 50-50 or 25-25, as long as the ratio to each other is still 1-to-1, that's indicative of bromine. So we eliminate C and D. Based on that M+2. So now using the 100% and 4.3%, we plug it into that equation. So again, because you see 4.3, you can eliminate choices C and D because the answer has to sort of hover around what that M plus 1% is. So if we take 4.3, divide by 100, divide that by 1.1, it gets you 3.909, which we're just going to call 4. So C and D are too high, and then 3.9 is closer to 4 than it is to 3. So the parent is 72. We just determined that n is equal to 4. So 48 mass units of that 72 belong to carbon. So what do we have? 24. We have 24 mass units remaining we have to assign. Is A a reasonable answer? Why not? It's way past the maximum number of hydrogens. So I'm gonna write this ad nauseum. You're gonna get sick of me writing CnH2n plus 2. But n equals 4. So we get 10. So for a saturated molecular formula, the max number of hydrogens you could have is 10. So 24 is past that. D as in dog is kind of unreasonable as well. Just using your Lewis dot information, if you had 4 carbons and you tried to stick in 2 oxygen and draw a structure, you'd have trouble forming the number of bonds required. So we're stuck somewhere between B and C. Both have 1 oxygen. And now we just have to figure out the ratio of hydrogens that's going to get us to 72. So the way we can do that, so 72 is all elements, 48 is carbon. Where is the eraser? Okay, here it is. It won't let me do it, sorry. All right, 24 is equal to H plus O. So that's 1, that's 16. We can't have 2 oxygens, right? Because that's 32. So if we say 1 oxygen, 24 minus 16, that gets us 8. So that is the number of hydrogens. So we get C4H8O is the molecular formula. So for N equals 4, there's a maximum of 10 hydrogens. That's the fully saturated alkane. We found C4H8. Remember that oxygen does not affect the hydrogen count. So that gets us to H2. We divide that by 2, so we get 1 degree of unsaturation. So if you had that molecular formula, 1 degree of unsaturation, now what we want to do is take that, start drawing some constitutional isomers. And the logical way to do that, we can say a degree of unsaturation is a pi bond or a ring. And furthermore, we said a pi bond can be carbon-carbon or carbon-oxygen. So which of the following is not a viable combination of functional groups that could be in that molecular formula? I think I heard C. Why is C not? So must have, I heard it in the audience, it must have 2 oxygens. So remember that an ester has a carbonyl. That's fine, that's a degree of unsaturation. But then you have this and then another oxygen. So the molecular formula only has 1. Only has 1 oxygen. We have a minute 40 seconds. The last slide is questions, but I'll just stay on this slide to help kick us off now that we have more information. How can we take C4H8O and let's draw a ketone? So there's 4 carbons. And now for a ketone that has a carbonyl, and it has to be internal in the chain. So that's a viable constitutional isomer. An aldehyde has a carbonyl, but it's at the end of the chain. So that could be one. Now here, cycloalkane, that would be the degree of unsaturation. So we could draw a cyclobutane, and then the oxygen would be part of an alcohol. For that, you could draw other constitutional isomers that have a ring, and I encourage you to do that and then name the functional groups present. But where we're going with this is we're going to use IR to say, okay, it has a carbonyl or it does not. It has an alcohol or it does not, because those signals look a specific way. And then for every constitutional isomer you draw, if you do the uniqueness of this versus the uniqueness of the aldehyde, you'll see that the carbon-hydrogen sets and the ratios are all different. And that will eventually lead us into NMR. So we're done for today. My voice is cracking. Don't forget to do your quiz.